Hey, good morning, everyone. Thank you for being here today for one more day in the second summer school of Blades to Build. It's a pleasure to have you here. I didn't have the chance to make an introduction yesterday, so I think there's a chance to welcome you and greet you in our premises. Hope yesterday you enjoyed the lectures and the interactive session that we have. Kate did an amazing job organizing all that. It wouldn't be the same if we didn't have her, to be honest. So thank you very much again, Kate, for organizing yesterday's day. So today we are going to focus mostly on lab activities. Yesterday we had the chance to see a few lines related to the recycling of composites, since also the lectures were covering this aspect. You also had the chance to see the fiber production line, the underground of the school. So today, my talk is related to things that you saw yesterday in the labs, and you are going to see today during the lab activities that we have prepared for you. So probably you've already seen in the program of the school of today that we are going to see quite a variety of processes related to composites and carbon fibers, mostly. So in order to be able to understand better what we are going to see later in the labs, I'm going to give you some fundamentals in carbon fiber composites, carbon fibers, more specifically. That way you can, even if you are not that much experienced within carbon fibers, you will have the basic knowledge in order to understand and maybe ask even questions later on during the lab activities. As I told you yesterday, we are going to have a more hands-on experience today in the labs, because yesterday we didn't have a lot of time. So without further ado, this lecture is related to carbon fiber production, structure, properties, and surface treatments. These are all the necessary processes in order to understand carbon fibers, how they are produced, and why we use them. So carbon fibers. Carbon fibers is a material which we produce in a fibrous form. It is composed predominantly of carbon atoms, more than 90%. The higher we get, the properties bring say in a way we are going to see later. And they are arranged, these atoms are arranged in a graphitic or in a turbostratic structure. We're going to explain what this is. Probably you're familiar with the graphic structure, with the planes of the graphite, which is called graphene. And we use them because they have exceptional strength to weight and stiffness to weight ratio. This means that they are very light and very strong, very durable. And this we can see it also from some of their key characteristics, like the density, which is around 1.75 grams per centimeters. A tensile strength that can go up to 7 gigapascal, and modulus that can go up to 900 gigapascal. They are also chemically inert and very stable thermally, because they are composed mostly from carbon. Carbon have superb thermal stability in this form. So in applications, we use carbon fibers in a wide variety of applications, more and more years pass. From aerospace to automotive and equipment in sports, civil engineering, and wind energy, of course. We talked a lot about that yesterday, how they are used in wind turbine blades. We saw mostly glass fibers. We talked mostly about glass fibers yesterday. Okay. We mostly talked about glass fibers yesterday, but this is due to the fact that Most of the traditional, the old wind turbine blades are made out of glass fibers. However, there are some sections like the spar, which is an internal structural section of the wind turbine blade. It is made out of carbon fibers. So they are also used in the turbine, and probably they are expanding as well. Okay, now we talk in the next few slides. We're going to talk about the production of carbon fibers, how we make them. This is a general overview that will give us the necessary feedback in order to understand each of the processes. Okay, to produce carbon fiber, we need a precursor material, something that we are going to transform into carbon fiber. And in the majority of the times, this material is the polyacrylonitrile, which is a polymer, of course, that it is manufactured in fibrous form. We have the pellets and we transform them in fibers. This is the bottom left part of the slide. We're going to see how we transform this polymer into a fibrous form later. And then through a consecutive steps of thermal treatment that we call either oxidation or stabilization. The first one is this, and then we move on the carbonization. With an optional step of graphitization, we now have reached the form of carbon fiber that we all know. But it is not yet 100% ready. We still need to perform some processes on the surface to make them endure everyday handling, the workers handling, but also improve their adhesion with the matrices that we use them, because I haven't said that yet, but probably you know, carbon fibers are not used in the fibrous format that we found them when we produced them, but we combine them with resins to make composites. Why we do that? Because you can understand that a fibrous material doesn't have properties in all directions, and also it is not a stable material. You can bend it, twist it, do many things with it. You can for sure put tension on it, and it's going to be good properties. But if we combine them with resin and make adjustments on the design and on the direction that we put those fibers, we can have exceptional properties in more than this one direction. And this is why we use them within the resins to produce the composites. Okay, and this is why we need these two extra steps to facilitate the adhesion with the resins that we use them. And in the end, of course, we have the winders where the carbon fiber spools are winded. And after that, we can do many things with these fibers. We can do them as they are to produce some composites with some traditional manufacturing techniques like filament binding or pultrusion, or we can make fabrics out of it. We call them mats, for example. And those fabrics, we use some traditional tools to form the warp and the web, to make 0-90-degree orientation of a fabric. We are going to see how these fabrics looks like, and the fibers, of course, later in the lab. So these processes that we discussed, the stabilization, carbonization, treatment, and sizing, all of them affect the final structure and properties of the carbon fiber. And we are going to explain how each one is affecting the properties. But for now, this is the general schema that I want you to keep. We said about polyacrylonitrile, which is the major precursor. We also have we are using pitch, mesophase pitch as an alternative precursor. It has differences in terms of processing and properties when compared with the polyacrylonitrile. We use them in occasions where we need higher modulus than the highest possible modulus and even better thermal conductivity. And historically, rayon was also used, but now it's obsolete. Basically, the carbon fiber was originally formed as an idea based on rayon precursors. Okay, so let's see how we get this polyacrylonitrile in a fibrous format. This is a process we call spinning, and there are different types of spinning techniques. We have melt spinning, which probably you saw yesterday during your visit when was the pyrolysis furnace. You saw an extruder where you put the pellets, and then there was a filler where you can extract the pellets into a fibrous format. So you are based on melting the polymer and produce fibers out of it inside the filiere. Okay, this is melting spinning. But for some polymers that cannot be melt spun, and this is related to their properties and how do they react when we heat them. We might need to do a different process like this one, which is called wet spinning. And specifically, polyacrylonitrile starts to degrade before reaching the melting temperature, and this is why we can't melt spun the polyacrylonitrile, and we choose the wet spinning. Wet spinning is a process, again, that ends up with the filiere here in the bottom left. But we take advantage of a solvent that we can dilute the polyacrylonitrile powder, and then the solution with the polymer enters a bath where the polymer is insoluble. So we call it precipitation or coagulation bath. And then the solvent that we have dissolved, the polymer remains diluted within this new bath, but the polyacrylonitrile starts to solidify. And through this filiere, we spin it into this fibrous format. This is called spinner as well. This is the process that is used in the industry to make polyacrylonitrile pellets or powder into fibrous format. So this is how we get this kind of material, the precursor of carbon fibers. And this is how an industrial pilot looks like for spinning polyacrylonitrile. Okay, then we move on the second process. Since we already have the fiber, the polyacrylonitrile in a fibrous format, we are going to talk about the stabilization, which is the first step in fiber production. Stabilization or oxidation is done in air, so normal atmosphere, and in a temperature range that rarely reaches the 300 degrees. I think it is close. It starts from 180 and can go up to 220. The goal is to transform this linear polymer, the polyacrylonitrile, this linear polymer into this ladder-like structure into consecutive steps of stretching and thermal treatment. And there they take place the cyclization that we saw, that for linear, non-linear polymer. cyclic polymer, cyclic structure, better, yes. And we start to remove some of the extra atoms that exist there, like the hydrogenation, the more atoms will be removed later on during the graphitization. So for now, our goal is to make it in a cyclic format and make it infusible. This is very important because later on, when we are going to increase the temperature, we need this material to withstand it and not infuse or melt. Okay, this is the goal here of the stabilization. It is also a very high energy step, especially in the industry. And there's also research taking place trying to either reduce the time that it takes or reduce the energy that it is demanding. This is a part of today's research. Okay, the final step on the thermal treatment is the carbonization. This is actually, we said that this is actually the process where the carbon fibers start to take the structure that we know and the look that we know. This is done in inert atmosphere. Normally we use argon or nitrogen, most of the times argon, because it is less reactive in those extreme temperatures. Temperatures can go up to 2,000 degrees, for example, in this step. So the fibers are getting pyrolyzed. This can also be done in a gradient step, so lower temperature and higher temperature. And this will help us progressively remove the extra atoms that I was talking about before. So hydrogen and nitrogen that are there in the actinolitrile structure are removed. And parallelly, the ladder-like structure that we saw before starts to become more ordered, which means that we are getting closer to the graphitic structure. Okay, so this I have it in the next slide. We are going to see how the graphitic structure looks like. If we need to further increase the graphitic structure and have it very organized and ordered, then we can proceed with the graphitization. It is an optional step, as we said. This will affect the properties, so we do that only if we want to have lower strength but higher modulus. So very specific applications. If need these kind of properties, then we are doing the graphitization, which takes place in even higher temperature, 2.5 K. Now we are going to talk about surface treatment. Surface treatment is a major part of our research in the group. We started it for more than 7 years. We had also several projects that we used to work on this field. It is necessary, not optional, and this process is necessary because we need to modify the fiber surface. Why we need to modify it? Because during the reaction that takes place earlier, during the stabilization or the carbonization, our fiber remains chemically inert. So we have these graphene planes that we discussed, this graphene structure, but these are not reactive in the resins that we use them. We don't have any covalent bonds that can form with the resins. And this is something that we need if we want to improve the adhesion with the resin. So this is why we are doing the surface treatment. We may also have some surface defects which can also be removed or can act as points to formulate the oxygen groups on their surface through these processes. And this is the important stuff here for the surface treatment. And as I said, we also have the sizing as a last step. Again, in the lab, we have developed several approaches to size the fibers. You are going to see them actually today, later in the lab. We have a pilot line for continuing size our fibers. During the industrial process, sizing is used to apply a thin film on the fiber surface, mostly to protect the fiber from environmental damage, and also to facilitate the workers during handling of this fiber. Because imagine that a carbon fiber tow can have from 3,000 monofilament up to 50,000 monofilament. Fiber is 7 microns in diameter. It's very thin, very tiny. So if bandwidth 6,000 or 12,000 monofilament didn't have any binding agent, let me say, to understand it better. When we would unwind it, things would go everywhere and wouldn't be able for workers to handle it. So industrially, at least in the industrial scale, sizing is used to facilitate the handling and protect the fiber. But in a research level, since this binding agent, which is a form of coating, let's say it's a polymer, and this can also generate covalent bonds with the resins. There's also research taking place there, since it's the external layer of the carbon fiber. We can modify it. We can decorate it with nanomaterials, for example. So this way, we can increase the area of the interface. And interface is a very important factor in comfort. Having a strong interface is really important because then we don't have weak interlaminar forces. The composites can withstand higher shear stresses, which is important. And we have developed a methodology in the lab. We have designed and produced a pilot line where we can treat fibers in a continuous format, and we can put carbon nanotubes that you saw Vangelis, for example, yesterday, synthesizing through soluble waste. We can use those carbon nanotubes inside the sizing solution that we have, and then apply this sizing solution on the fiber surface. Okay, so you see here another example of how we try to connect our processes, starting from the solid policies, where we recycle the matrix, and then the fibers are reused into making the composites, or the liquid byproducts are reused in the CVD reactor to make carbon nanotubes. And then we get these nanotubes and put them into sizing solutions. So we decorate the recycled fibers, for example, that we got from solubilities, and then make new composites that would have better properties than using, for example, resins, recycled fibers without any treatment. So this way we can close generally the loop, let's say, with quite popular catchphrase within our lab. Now, the surface treatment, I said a few things about it, but we need to understand why it is also, what are the challenges that we need to face. Okay, we said, maybe we didn't, that when we have this composite with the resin and the fibers, and we apply a load, we stress it for the purpose. It's getting stressed. These stresses are transferred through the matrix in the fibers, and we need this strong bond between the fibers and the matrix in order to be able to effectively transfer these loads inside the fibers and don't fail in the interface. Okay, this is why we said we need the surface treatment. For example, here we can see a reference fiber, which looks quite good in my opinion. And then we try to put some other uglier stuff on the surface. But sometimes these uglier stuff have a positive impact on the interface. However, we need to be very careful because there's a sweet balance spot during the surface treatment that we need to consider. And the ideal adhesion that we can get. Because if we treat in an extensive time, then we can damage the fiber surface, and this will lead us in a fragile composite. It will fail earlier than it would without altering the fiber surface. If, on the other hand, we leave it, for example, in very few minutes or seconds, then we will not have any significant effect, and we will have a weak treatment, and so there will be no changes on the adhesion. That will also lead to a lower than intended composite durability in the composite. So what we need to do to call a treatment successful? First, we need to increase the wettability of the fiber surface with the matrix resin. This means that the matrix, which is a liquid format, can easier let's say tangle all of the fiber surface area. Okay. And this is often used. This is often achieved through engineering the weak boundary layers, which might have some contaminants or absorbed gas molecules which right there during the stabilization and the carbonization phase. Another important aspect is that with this increased roughness here, with this increased roughness that you see, we enhance the mechanical interlocking between the fiber and the matrix. Okay, these are some features on the surface where the resin can penetrate and then interlock the reaction. When it is stressed, this interlock facilitates makes it harder to break. And this is achieved through increasing, for example, the surface roughness, which leads to higher surface area, more area for the resin to be applied on, and subsequently higher mechanical interlocking. There are quite a few options to treat fibers. We are not going to stay all of them today. The popularity decreases as we go right from the clock. So electrochemical oxidation, and plasma are treatments that I have also witnessed in my career, and they are also used in the industry, especially the first two during the industrial production of fibers. It's and the two last are the gamma treatment and the rare element treatment, but more in the research level than industrial. Oxidation, I don't have to explain a lot of things to understand how this works, but Either we have an oxidative medium, either in a solution format or in a gas format. And by adjusting the concentration of the medium, the time and the temperature, we can modify the fiber surface by putting oxygen groups on the fiber surface. Some of the mediums that we use are as well. And generally, oxidation can be a good starting point for further treatment. So, for example, you see here that it's called started with a simple oxidation process with nitric acid, where he attaches hydroxide groups on the fiber surface, and then through consecutive steps, he reaches this kind of structure, which seems quite impressive, but he has something specific in mind. We don't usually see this kind of stuff in the industry. So is maybe in a very specific application, this can be applied, but it's a good starting step to further oxidize the fiber. Electrochemical oxidation is also a very popular approach, also in the industry and in our labs. We worked a lot with this process in the past. Spiros as well, who is also the next speaker, has worked a lot generally with electrochemistry. So him or me in the break, if you have some questions. The difference, we use again some mediums, oxidative mediums. The difference is that we also apply potential, polarization potential, and this can also take place in cycles. So we can do cyclic voltammetry, for example. I will not stay into very many details here. You can read some of our papers or ask us if you want to read more. But the idea behind it is linked also with the structure of the fiber. But the idea is that through electrochemical oxidation, we can put through the graphene layers of the carbon fiber some of these oxygen-containing groups. And this will facilitate the covalent bonding that we can have with the resins that we said before. Okay, some of the parameters, of course, that we need to fine-tune is the type of the light, the permeable solution, the polarization potential, and of course the duration of the treatment. These all will affect the morphology of the surface. And for example, here we have to be also very careful to not overdo it because we will damage the fiber. It's a common example here in the electrochemical oxidation because we don't only apply the oxidative medium, but we also have the potential that we apply. So even harsher conditions for the fiber to withstand. But this can also, since we know the chemistry behind all these reactions, in which potential they take place and how much time it is needed, and we can also read the graphs to understand what takes place. If someone has the knowledge and the know-how, he can be very successful on his treatments. So you saw that all of the different processes that we discussed here today of reaching the final carbon fiber that we can find in the market have its own purpose and it affects a lot the structure of the fiber. So the precursor that we are going to choose is going to, for example, play a major role because it affects the structure that we get. And also different precursors have different yields. Since we are talking about the carbonization process, we are transforming a polymer into pure carbon. This has an effect. The structure, the precursors that we choose have an effect. Different precursors have different yield on this transformation. Okay, the spinning and the drawing, this is how we transform the precursor into the fiber, and the tension that we apply have an effect on the diameter or on the orientation, and different precursors exhibit different kind of defects. The stabilization adjusts this ladder structure that we saw, and is responsible to make the polyacrylonitrile infusible, so it can withstand the high temperatures of the carbonization and graphitization, which transform this polymer into the carbon fiber format with the graphitic structure. It creates this ordering that we discussed, and it removes all the heteroatoms than the carbon. Lastly, the treatment and the sizing affects the wettability that we said, specifically treatment, the handling through sizing, and both of them combine their compatibility with the matrix. And this is an example of a very famous lab from Oakley. This is how a closed industrial line, let's say, would look like, of producing fibers. This is quite long, as you see, even though it's not an industrial line. This is quite long because all of these processes require a residence time, special stabilization, and all these reactions, all these processes take place parallelly, one after the other, because it is a continuous process. So starting from the very left, we would have our precursor, our polyacrylonitrile, and then through consecutive steps without removing the spool, because every time a spool passes through a winder, we lose part of an amount of filament. So this is why everything takes place in one shot. It's important. Each time we wind the fiber, we lose some of the filament. It's how it goes. Even though they are very strong, they're still very tiny. 7 microns. It's the diameter of a single fiber. I'll try not to bother you too much with the structure, but it is important to understand all the things that we said, and it will help you understand why we're doing the treatment. Here on the left, we can see how the precursor looks like, and how it looks after the stabilization. And let's stop here in the carbonized yarn phase. So we see the hexagons here with the sp2 bonds. Okay, sp2 are the bonds that forms carbon. This one here. If not, I can explain it more later. But you see some defects like this one, and you also see they're not very aligned. They are not continuous. They have a wavy format. So this structure here, this wavy structure with the graphitic or structure but with defects is what we call the turbostratic structure. Because they are not they don't exhibit a perfect crystalline graphitic structure. Graphene layers are misaligned or randomly stacked, like, for example, here you see, or here. The spacing, which in classic graphite this spacing here among the planes. Then we call it interlayer spacing. This spacing is greater than the ideal graphite. So there's a bit more distance among the layers than in regular graphite. And this is what we call the turbostratic structure. Now, how we characterize it? With a degree of crystallinity. So the more closer to the graphite, to the ideal graphite structure we are, the higher crystallinity we have. This, of course, affected the properties of the materials. And specifically, it increases the modulus. So we have stiffer material because the load is transferred better and easier through the structure, but we also have less strength. And this takes place, this happens specifically because in the less ideal structure, for example, here in this defect, the load that is applied, the stress that is applied, will have this barrier there. So it will not be so facile. We will not facilitate the movement of this load, the transfer of this load. This acts as a barrier during load transfer. And the cracks do not propagate that fast and that easy as in the perfect crack. And this is why we have lower strength in the higher crystallinity level we achieve. So going back originally, I discussed about polyacrylonitrile and pitch, and I told you that pitch has greater modulus. So you would expect that a pitch-made fiber would have a structure closer to the ideal graphite, okay, higher crystallinity. While a fiber coming out from PAN and without graphitization, only carbonization, would have lower modulus but higher strength. And we explained why this happened. Why this happens. Okay, and one last thing I didn't mention yet, because the rest will be, is that the properties of the fiber have significant differences along and across the axis, along and across the graphitic planes. Okay, so along the graphitic plane is where the fibers have their very good properties, because this is the carbon atoms are connected through the sp2 bonding that we discussed. Okay, while across the fiber axis, through this axis, we only have some van der Waals bonds, which are quite lower comparing to the sp2 bonds. Okay. So this is why the properties differentiate a lot along and across the axis. And this is applied for all the properties, not only the mechanical, but also to thermal and electrical. And this is due to the, for example, for the electrical conductivity, we have the sp2 bond, which gives us a free electron to transfer the electricity, yes. So this electron can move along the planes. Okay, so this gives us a high conductivity material on the axial direction, while on the transverse, where we don't have any free electrons, actually we only have van der Waals bond, keep these planes together. We will have very poor conductivity. Okay, to sum up, there are a lot of fields of research taking place nowadays. We are looking for alternative applications. We also have a project called Suspense, where you saw what you saw yesterday from Kate. There we study more environmental friendly precursors like lignin blends, which can be stabilized and act as a precursor for carbon fiber. Faster stabilization times, I already said how energy intensive this process is, so we need to do it faster. Also, the treatment and the sizing, it's an easy step to do. It doesn't require a lot of, especially if you do it on large scale, it doesn't require a lot of investment to try different methods. In the field of resin as well, we are using a lot of greener resins. You saw yesterday how complex it is to recycle the thermoset resins due to the crosslink. So we are looking for alternatives like determinants. I know someone was very different yesterday. These are things that we can reshape them through heating or cleavable bonds. Another approach would be that, or more bio-based resins, which are still thermoset and hard to recycle, but they have a lower environmental footprint. That's all I had to share for you today. I hope you have a better idea of how these processes work, and we help you prepare for the next lab activity that we can, and the next speaker as well. So thank you very much, and if you have questions, you can feel free to ask them now, or we can discuss them later during the lab tour, for example. Yes. Sorry, just wait a minute.
I wanted to ask in the first slide about the applications in aerospace, in turbine blades. Do you have any idea in which stages of the turbine are they used on? Yeah. It's in the later stages or in the stages in the rotor and stator of the pair?
I'm not sure I can answer that. I think that the blade is made out of CF in the rotor, yes.
Yeah, okay.
He's talking about airplane blades. Not
in the engine, if I got correct.
Yeah, in the end.
Okay, thank you.
I wanted to ask in what kind of applications do we prefer the more graphite structure?
Where we need very fast transfer of heat. So in pedal brakes, we have this kind of programming. Also in brakes, we use a lot. Or it can bounce as well. We find that something to touch.
Hey, thank you for the presentation. I want to ask the ballistic application for the graphene utilizations, because you know that the ballistic applications, the load capacity is really important. Can you give us if possible, can you give us the examples for the graphene? Is this possible or not? First, my question.
I'm not sure. For sure, they use Kevlar fibers in this kind of applications.
Yes, a
because
kind
they have
of
higher impact properties.
Yes, and also carbon can be used, but as you say that the graphene has a capacity for the load. the energy dissipations. Therefore, with the carbon fibers, with I mean the surface treatments, the graphene can be usable for the not
I'm
the
not sure we can treat the fibers in such a way to be able to withstand the impact properties or to compare them.
okay. Thank you.
It's limited the things that we can do on the surface. Maybe we can try a few things on the lab level, but still for industrial would require some time.
Okay.
But
Thanks.
yeah, if you have some ideas, we can discuss them and see if we can do something with the equipment that we have in our premises.
Thank you so much. Thank you.
Other questions?
I was just curious to know whether the surface treatment using CNTs are cost effective. For example, if let's say if we use the same surface treatment for aerospace or automotive industries, we also need to think about the cost effectiveness, right? So do you think it is cost effective?
Exactly. In what quantities we are going to use them, what kind of effect they will have on the final properties of the component that we build, how it will impact application or its service life. I wouldn't be able to say yes or no. I say you need to study with in an application level to be able to have a clear picture. For sure, what we can say in the lab, we have proved that we can do that, and also in a continuous level. We have also used it in some applications, in some demonstrators, let's say, in some projects. So we were able to make some real components out of it. But yes, for economic efficiency, I think we need to speak case by case with the client, be able to have a solid answer about that. Yeah.
Yeah. And also, I think we need to be also very careful while handling such carbon nanotubes.
Yeah. But I think we have quite a good experience, because they are used quite a long time. Okay, so yeah, we have some strict rules while using fibers format in such with such diameters. So also we can handle them with a proper care, of course. Yeah.
Good morning. Sorry for the delay. Unfortunately, I had a small technical difficulty in the morning. When I came to the university, I worked yesterday with the presentation. I have finished it, but unfortunately, when I tried to upload it, I realized that in the typical check that it was a former version, and I had to scramble to finish it. So let's start. We have the problem with as far as you know, since we talk about composite materials, we have the increasing the demand is continuously increasing, and this is not a secret. There is the size of European composites. The market in European composites is about 110 billion, $20 billion, and in 2022, and it's expected to grow with a rate of about 6% for up to 230. You can see here an indicative graph about this growth for Germany, which is typical for the entire world. And you can see here that there is an increase for almost every sector where you can find composite material. And this can attribute to the increasing demand for lightweight materials across diverse industries, such as automotives, electronics and electronics, with the reactor we will later, and several. So there's a large increase of the need for carbon fiber for composites generally. And this it is meant that this growth will lead to the problem with the end of life of these materials. You can see here, for example, that the expected volume of decommissioning made in Europe, which is expected to reach the value of almost 50,000 tons per year by 2030. Right now it becomes certainly a problem. At the same time, this problem is actually a hidden opportunity. Since most of the times the failure of a composite is due to the matrix and its deterioration. So the reinforcing fibers remain practically intact. This means that they also represent a high added value product that could and should be utilized. You can see here, for example, the expected growth for the recycled carbon fiber market in the USA. When it's expected to have a growth of about an annual growth of almost 30% for the following years, following decade. So it has a lot of good opportunities to grow. So in order to recycle the composite, the fundamental problem is the efficient, for its efficient recycling, is to find a way to remove the matrix. However, the matrix, in the majority or in the wide majority of the cases, is a thermostatic volume, which means that, it does not melt, it does not dissolve. So we cannot use heat in order to remove, to melt the polymer so that it can be removed, or we cannot use any kind of solvent to remove this material. Thus, the separation of the two phases, it's not an easy task. However, there are already several methods proposed for the fiber composites. As you can see here, for the case of carbon fiber composites, which is typical for any other import material, the most non-productive way is land filling and the incineration. Land filling right now is considered the way that it has to we try to stop it. We have lots of regulations right now in all over the world, and they try to avoid to make land filling of composite red material economically environment. So they try to make it less okay solution and pressure in order to have some better solution to utilize composite. Incineration also is it's not very good because the only thing that we can actually achieve is part of the energy. Energy inside the material recover, which is not exactly 100%, so it's not very good. And you also have the problem with a lot of number of gases products which are multi-toxic, and you have also the carbon dioxide problem. There is also mechanical, those that they are considered recycling methods. The most well-known are the mechanical method, where you take the composite and you break to smaller chunks or stuff to write it, and you have a fragment of the composite which can be a pillar or something like that. And then we have what is the core of the modern and recycling technology. These are, okay, we have two large groups, which is the thermal and the chemical. And another group that we would like to grow on the following years is the other. Thermal methods, the most well known is biology, where you actually have already talking about that, there is also that reminded here. When you have biology, what you do is that you burn out the organic material, remove the organic material, which is the matrix, and you are left with the inorganic material, which typically is the reinforcing fiber, be it glass fiber or carbon fiber. There are also some differences about the biology. Fluid type is more for thermolysis, which is a kind of the same as biology. And gasification, where you actually try to take part of the matrix as a gas byproduct. So it's some kind of material. Here you actually what you take out of biology as a final product is the shortcut of fiber or this computer what much more property because it depends on the conditions of the composite. Then you have the chemical methods. Here we have thermolysis. Thermolysis is not typically not chemical method per se, because actually the solvents they are in normal conditions, they are not reacting as agents. So in order to import them to be reacting, we have to go to harsh condition, high temperature or high pressure, a combination of both. Electrochemical methods, you can actually sometimes they are together, but it is a completely different method. Here, the problem is that you have to find something that would be conducting. Otherwise, misunderstanding that I showed in the literature before about the electrochemical method. Which is actually when you have a material that is not conducting, you cannot use, you cannot say that you use electrochemical method in order to for example, I realized I tried to say that electrochemical decomposition of the polymers. But they use water that is as high as 10 kilovolts in the solution. So this is not changing the chemical method. Actually, like I call that very solution. And generally, there are several other methods like titration and acid titration. So the other method is they are right now they are investigated right now as a solution or dynamic fragmentation. Some other techniques that they are very technical. Generally, there is a lot of research on this field, and they try to find a lot of methods. Here you can see a typical table about the advantages and disadvantages of each method. I will focus on the case of the chemical recycling. Here, the main advantage is that you have the fiber side that we can have. The size is the length of the fiber that we can actually receive by chemical recycling is quite big. And you also have the advantage that the fiber is oriented with dangerous contact, so that they are not in the case of mechanical recycling. And theoretically speaking, you can also use the rent market in a way, if you are like that. The disadvantages are the long reaction time, which is typically for the case of room temperature treatment, reaction. We have strict recycling conditions here because we have to find a way to, since we will use some chemical agent, we have to also hide by the environmental issue. The cost of the solvent is typically high. I'm not sure that this is 100% true. However, this is always true. The waste liquid is toxic and difficult to treat. Most of the time, most of the time, the liquid that you receive from the liquefied product is toxic. It's very difficult to handle. This way, it's not very environmental friendly. But we still we try to. So these are the problems with chemical recycling. At the end, the selection of the proper recycling method relies in the combination of technical and the economic terms. When I say technical, it means the nature of the raw material. When you have a composite that is already in the form of continuous, you have in the form of a large item, then you have to use a method that can actually receive most of the as much as the material is intact, most of the fibers of the cloth that is used in order to produce it. If you have a polymer a composite that is already milled and is in small chunks, then there is no need to use. Then in this method, you can use some more a cheaper way to remove to retain the final material. So in that case, you have the energy cost, for example, to be the driving initiative, the driving force in order to select the determinant. The aim of this presentation is actually to present the primary research results from our laboratory in two promising recycling methodologies that we developed recently. The first one is formic acid hydrolysis for recycling wind blade waste. This is 3W. And the second case is electrochemical treatment as a method that could be efficient for recycling carbon fiber reinforced polymers. The first case, the formic acid, here what happens here is that the main chemical recycling methodologies are separated mainly to solvents and digestion. In the case of solvolysis, you use solvents at high temperature and/or pressure in order to achieve the desired result. And in the case of digestion, you use corrosive solution, normally concentrated in organic acids like concentrated sulfuric acid. The main idea of using formic acid is that it's more reactive than the organic solvents and also more corrosive. Actually, it's like combining the two methods. The flow sheet of the process you can see here. We start with the initial raw material, then we pass it through a shock slate where we have the formic acid. Then we have the washing. We wash it with water, followed by drying, sintering in order to, because even after drying there is a residual polymer on top of the waste. So we have, in order to remove it and retain the final fiber, we have the sintering process, and we have the final product. So a couple of details about the process. The initial waste we used it was one with the largest fractions. We have received this in the place of in the framework of the Blades to Build program. We have received a number of waste in blade fractions. They have already been from milling wind blade and making to smaller chunks, and then they sieved it and had different fractions, different size fractions. The one we used here was the one with the largest size part, which is it was written that it was above 20 millimeters. So Soxhlet, why did we use Soxhlet? I'm not sure if you are familiar with that process. You will see later a picture of how this actually works. But it was selected initially as a stopgap method. There is actually here I had inserted some. I didn't find. This is one part where I lost a lot of things here. I had to explain it verbally. There are some. There was our initial idea was based on a paper where a group tried to use formic acid in order to dissolve and retain carbon fibers from carbon fiber composite. And they used they dissolve it at room temperatures. So they needed about 20 to 30 hours, which is economically unviable. So we decided we tried also with our samples, and we realized that it's not very fast. It needs a lot of time, and it's not very efficient. So we also have the autoclave we use for solvolysis. But it's also too expensive and very difficult to use. So in order to avoid using this as a in between, we used Soxhlet, which actually permits the reaction to proceed at boiling temperature, which is actually the highest possible temperature at one atom, at room temperature pressure. Then that's about the Soxhlet. Washing was needed because formic acid is acid, so we had to remove it after the treatment, and we had to wash it with tap water, low, until we reach a pH value of 4 or higher. Afterwards, we had to dry the material in order to have faster drying. We realized that it was vacuum drying better because it was faster at 51 degrees Celsius, and it took about 1 to 2 hours. And finally, we have sintering in order to remove the residual carbon material on top of the glass fiber product we had to obtain from the wind blades. And it was at 650 degrees because there is some, it doesn't need a lot of time. But we have there are some persistent organic chunks on top of the material, so we have to avoid that. Generally, with waste, I had to actually use before that. The overall yield it's about around 65%, depending on the case. Now I have to actually say a lot of things about the raw material, which was we used in the Blades to Build. Initially, we thought that it was mainly composite based on glass fibers with polyester, with saturated polyester. It had the characteristic odor of styrene, which is typical for unsaturated polyester. However, we realized during this soft slab treatment that in reality we had a combination of different composite materials. They are different rails and matrix that were used, and that made it made the recycling difficult. What was the advantage of using formic acid was that it could actually dissolve any kind of matrix we had. So in the end, we received the final material. However, we had to go through sintering because there was a small amount of organic material still that was not removed. So we had to burn it out. And the overall gain was the result of the amount of inorganics on top of the fibers. Generally, even with the other methodologies we used, solvolysis or pyrol or thermolysis, this was the overall gain, around 60%, was due to the material we used. We have here a spherical, when we put the vessel, glass vessel, when we put the solvent here, actually it's a formic acid, not a solvent, but it's the liquid. On top of that, we have this reflux vessel, which we put here the material, and on top of that there is cooling. Sorry, so it's a cooling. Sorry, I don't remember the exact right now. So what happens that this solvent boils, it goes through here to the cooling, and then becomes a vapor, and then as a vapor is puts down to below boiling temperature, have forms that appear on top of inside the vessel when the level of the solvent reaches this point, then you have reflux, and it returns back to the boiling vessel here. So what happens is actually you have a continuous reflux of solvent during this method, this process. The result is that you always use a new solvent that not stays here, does not stay not static, and you have a continuous flow of solvent using the same amount from the beginning. Here you can see how is the material packed when we put it here. I don't know if you can see that. In fact, the chance of it. You can see here it's about 4 to 5 centimeters, and even bigger. You find about 30 centimeters, for example. And we pack them inside the main chamber, the soxylate chamber. You can see that after a couple of reflux the material has already been separated to its fibers here, and you might see that it's a bit color. Generally, it takes when the thing is colorless, the matrix, but that after a couple of rounds, it turns into bluish or green or greenish color. And in the end, this is the final look, the final liquid that we have as a byproduct. Actually, this we have it's a very difficult to exploit. We find a way to do it. We try to fractionate so that we might receive something that is already deployed, but it's not. It does not. It's, we didn't manage to actually remove anything. We use the water solutions in order to dissolve the organic sample that we have there inside the whole under the whole reaction, but this did not give any reason, any kind of so we don't have, but however, the problem, the good thing is that it's very stable. This, I have already, we have already did it for 1 year and it has not any problem. It's very stable. Have not seen any kind of separation. Now, as I've already told, the material we have here, the material, it's not, we don't say much exactly, but we are, we know that there is a combination of different matrices. So that we have to see, since we use formic acid, we have to see where this will react. So you can see here that the molecular structure of the common amine epoxy system, which is the most well-known combination of DDS crossing. Here, as you can see, as you can see, the main regions where the main links where they can be attacked, the epoxy amine. These are relatively stable structures, but they can be attacked under harsh conditions. And in the case of, in our case, the most probable reason that this matrix is dissolved is due to the attack of the folic acid with the reaction with which is acidic, and the react with the amine, which is a base. So we have something like a neutralization reaction. Leading to the opening of this bond and actually creating smaller and smaller parts of the solution. The problem. Then we have another possible material that could be inside the inside is the anhydride epoxy, anhydride epoxide. It's some kind of epoxide that also welding. And here we have BA with a cycle of hexamethyl with carboxylic anhydride. In that case, the ligands here are ester ligands. They are not very, they are very special. And when we have ester, it's generally considered that they are weak bond, and they are very easy to clean. They are very easy to clean. So in that case, as well in the next case, which is probably the most majority of the matrix used, was unsaturated polyester. Here we can see the structure of unsaturated polyester before curing. You can see this is a linear. It's not actually it's not linear. It's actually a close link. So not like that. But however, you can see here that we have also ester ligands, which are also saturated ligands. And in this case, in both these cases, formic acid acts as a reagent in order to cause transesterification. What happens here is that actually opens a lot of these things, a lot of these ester links, causing to create some kind of acid, and moving making another ligand with putting another ester in here. formula. So this actually works pretty well. And in the case, in our case, I think that what we managed to achieve is because we used this kind of reagent, very active reagent, and these conditions, we managed to dissolve completely the polyester, because some of the large majority of the chunks that we saw after the treatment, they were almost completely clear of any kind of coating. However, we have from the other matrix, you have to remove the plastic of the matrix that we remove, so we have to perform the final step, which was kind of a fusing. So this is the second case, the electrochemical treatment for recycling carbon fibers. Here, the idea is to actually take advantage that carbon fibers have a high electric conductivity and post-partial or total delamination of the fibers and the matrix through electrochemical degradation, or actually or chemical or chemical. So we investigated different conditions. Here, the process was actually we used a carbon fiber composite that contained 60% of reinforcement in the form of a cloth made of plain wave cloth. It was manufactured with the typical vacuum-assisted transfer molding we use in the laboratory. The electrochemical treatment was performed using a potentiostat. We use the 3-electrode setup. For those who are familiar with electrochemistry, 3-electrode setup, you use you have your material that you have to you want to investigate as the working electrode. You use another material, commonly used as another metal, commonly electrode, which is normally used platinum plating, which is very electrochemically inactive, so you don't have any kind of side reaction happening on that surface. And this is the counter electrode. And you have the reference electrode, and here we use silver chloride, which is typical for that cases, as a reference electron. What happens when you have the 3-electrode setup? What happens is if you have 2 electrodes and you try to make an electrochemical reaction, what you have to do is that you have to overcome potential hardening in order for the reaction to take place. However, you also have to consider the ohmic reaction of the electrolytic solution. This is most of the times very high, even if you use very concentrated, very high electrolyte solution with high concentrations of electrolyte. You will not be able to overcome this ohmic resistance very easy. So you have to impose very high potential in order to have some current to pass through the 2 electrodes. So if you do that, you have, for example, when you have a reaction taking place at 1 volt and you go to 10 volts, then this reaction will take place at very high overpotential, and it will not be easy to control, or the final product, it will not be the one that you want. In order to overcome this problem, we use the 3rd electrode, which is the reference electrode. This is considered as an electrode that is cannot let any current pass through it, and it keeps a certain voltage stable. So if you have when you keep the distance between the reference electrode and the electrode stable, so you can change the potential of the electrode, and at the same time you use the charger electrode and the voltage electrode in order to measure the current that passes through the system. So you have two parts, one part which you impose the current, the voltage, and the other part that you measure the current. So you don't have to take this actually bypasses the problem of the ohmic resistance of the solution. What we investigated here is cyclic voltammetric conditions. In that case, what you use is that you don't have a stable potential. You use you sweep potential. You start from an initial value, then you reach a final value, and return to the initial value with a certain scaling rate. And after it's testing, the carbon fiber composite was thoroughly washed in the still water acetone in order to have force. The first thing that we tried was with sodium hydroxide solution, because this kind of it is generally known that epoxy resins are not very stable when attacked. They are attacked by basic solutions. So we try to use this sodium hydroxide. You can see here that as the number of the cycles increased, so the active current increased. The area close between the curve of the cycle goes down. And this is an indication that this is either that the surface of the carbon fibers or the electrochemical activity or both. However, upon optical inspection, there was no indication that the matrix disintegrate. So the component remained almost the same. So we realized that this does not work, and you can see here also after using with micro CT scan, and you can see here that the treatment, even though it's possible, the micro CT show that the composite sample remains intact even thereafter, it's the same as the initial. Then we changed, we went for acidic solutions, and we here have almost this. We have here, you can see here, we have different and even better increase of the active current. And the rationale here of using acidic solution we use here is actually to the uric acid solution, the carbon fibers are oxidized, and we have a cycle of oxidation, partial reduction, partial oxidation, partial reduction. So they are. We know that their surface changes. So in order to do that, and you can see here that we managed to increase the active current increased considerably. And it's more dominant than the basic solution. So it's evident that the electrochemical activity of the carbon fiber composite increases during this treatment. We also observed that during the treatment that the solution of the sulfuric solution we used progressively darkened. When we started with a solution that had no color, it was colorless, and then became starting during the treatment, it became pale yellow, and then at the end it's the dark brown. As well, the end here we can see that M3P analysis, the photographs from M3P showed that we can see here that the complete that the epoxy resin was removed both from the outer surface, which was a surprise for us, from the bulk of the sample. This is clear proof that the electrochemical treatment can be an efficient method for recycling the carbon fiber components. So this is what the concluding remarks is that in order to try and find the cycle of components is generally big headache, and it will be continue to be something like that. We have to investigate different methodologies in order to find the best one. And probably we can actually see that some seemingly easy solution might be as efficient as some less as efficient as more sophisticated ones. That's all I have to say for. I don't know.